Astronomy. Astronomy is the scientific study of everything in the universe beyond Earth's atmosphere. This includes objects we can see with the naked eye, such as the sun, the moon, planets, and stars, as well as distant galaxies and tiny particles that require telescopes and other instruments to observe. Astronomy is a diverse and interdisciplinary field that combines elements of physics, mathematics, and chemistry to understand the origins and evolution of celestial objects and phenomena. It covers a wide range of topics, including cosmology, stars and galaxies, planets and moons, astrobiology, cosmology, investigating the origins, evolution, and eventual fate of the universe as a whole. The Big Bang. The universe began approximately 13.8 billion years ago with the Big Bang, a colossal explosion from a singularity, a point of infinite density and temperature. This event marked the beginning of space, time, and all matter. In the first fractions of a second, the universe expanded exponentially in a process known as cosmic inflation. During this period, the universe cooled rapidly, allowing the formation of subatomic particles and simple atoms. Formation of the first elements. As the universe continued to expand and cool, protons and neutrons combined to form the first atomic nuclei in a process called nucleosynthesis. This occurred within the first few minutes after the Big Bang. The primary elements formed were hydrogen, helium, and trace amounts of lithium. The cosmic microwave background. About 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms. This event, known as recombination, allowed photons to travel freely, creating the cosmic microwave background, CMB, radiation. The CMB is a faint glow that fills the universe and provides a snapshot of the infant universe. Formation of stars and galaxies. Over the next few 100 million years, regions of slightly higher density in the universe began to collapse under gravity, forming the first stars and galaxies. These early stars, known as population 3 stars, were massive and short-lived, ending their lives in supernova explosions. These explosions enriched the surrounding gas with heavier elements, which later generations of stars incorporated. The present and future universe. Today, the universe continues to expand, driven by a mysterious force known as dark energy. Galaxies are moving away from each other, and the universe is becoming increasingly vast and cold. The ultimate fate of the universe remains uncertain, with theories ranging from continued expansion to a possible Big Crunch or Big Rip. The history of the universe is a testament to the incredible complexity and beauty of the cosmos. From the initial moments of the Big Bang to the formation of stars, galaxies, and planets, the universe has undergone a remarkable evolution, leading to the rich and diverse cosmos we observe today. 2. Stars and galaxies, exploring the life cycles of stars, the structure of galaxies, and the vast distances between them. The life cycles of stars. The life cycle of stars is a fascinating journey from birth to death, influenced primarily by their mass. Here's an overview of the stages a star goes through. A. Nebula. Stars begin their lives in nebulae, which are vast clouds of gas and dust. Gravity pulls the particles together, causing the cloud to collapse and form a dense region called a protostar. B. Protostar. As the protostar continues to collapse, it heats up. When the core temperature becomes high enough, nuclear fusion begins, converting hydrogen into helium and releasing energy. This marks the birth of a star. C. Main sequence. The star enters the main sequence phase, where it spends the majority of its life. During this stable period, the outward pressure from nuclear fusion balances the inward pull of gravity. Our Sun is currently in this phase and will remain so for about 10 billion years in total. D. Red giant or supergiant. Once the hydrogen in the core is exhausted, the star expands and cools to become a red giant, for stars like the Sun, or a red supergiant, for more massive stars. In this phase, the star fuses helium and other heavier elements in its core. E. Final stages. The final stages of a star's life depend on its mass. Low to medium mass stars, these stars shed their outer layers, creating a planetary nebula, and leave behind a hot core that cools and contracts into a white dwarf. Over billions of years, the white dwarf will cool further to become a black dwarf. High-mass stars, these stars undergo more complex fusion processes, eventually leading to a catastrophic explosion called a supernova. The remnant core can become either a neutron star or, if massive enough, collapse into a black hole. Interesting facts. Supernovae, these explosions are so powerful that they can outshine entire galaxies for a short period and are responsible for creating many of the heavier elements in the universe. Neutron stars, these incredibly dense objects are composed almost entirely of neutrons and have a radius of about 10 kilometers but a mass greater than that of the Sun. Galaxies. Galaxies are immense systems composed of stars, stellar remnants, interstellar gas, dust, and dark matter, all bound together by gravity. They vary greatly in size and structure, ranging from dwarf galaxies with just a few billion stars to giant galaxies containing up to 100 trillion stars. Galaxies are categorized into three main types: spiral, elliptical, and irregular. Spiral galaxies. Example, Andromeda Galaxy, M31. Description: the Andromeda Galaxy is a classic spiral galaxy and one of the closest to the Milky Way. It features a prominent central bulge and well-defined spiral arms. Spiral galaxies like Andromeda are characterized by their rotating disk of stars, gas, and dust, with new stars forming in the spiral arms. Elliptical galaxies. Example, Messier 87, M87. Description: M87 is a giant elliptical galaxy located in the Virgo cluster. It has an almost spherical shape and lacks the distinct structure seen in spiral galaxies. Elliptical galaxies contain older, low-mass stars and have little gas and dust, resulting in minimal new star formation. Irregular galaxies. Example, Small Magellanic Cloud, SMC. Description: the Small Magellanic Cloud is an irregular galaxy visible from the southern hemisphere. It lacks a defined shape and structure, appearing chaotic compared to spiral and elliptical galaxies. Irregular galaxies often have regions of active star formation and can be influenced by gravitational interactions with other galaxies. Most large galaxies harbor supermassive black holes at their centers, which can influence the motion of stars and gas within the galaxy. Galaxies are not isolated, they often exist in groups, clusters, and superclusters, interacting and sometimes merging with one another. These interactions can trigger bursts of star formation and significantly alter the galaxy's structures. The observable universe contains an estimated 2 trillion galaxies, each a unique and dynamic system in the vast expanse of space. What is a black hole? A black hole is a region in space where the gravitational pull is so strong that nothing, not even light, can escape from it. The boundary around a black hole beyond which nothing can escape is called the event horizon. Types of black holes. Stellar mass black holes. These form when massive stars, more than 20 times the mass of the Sun, exhaust their nuclear fuel and collapse under their own gravity. This collapse can trigger a supernova explosion. Supermassive black holes, found at the centers of most galaxies, including our Milky Way. These black holes have masses ranging from hundreds of thousands to billions of times the mass of the Sun. Intermediate mass black holes. These are less common and have masses between stellar mass and supermassive black holes. They are believed to form through the merging of smaller black holes or the collapse of massive gas clouds. Formation and growth. Stellar mass black holes form from the remnants of massive stars after a supernova explosion. Supermassive black holes, their origins are not fully understood, but they may form from the collapse of massive gas clouds or through the merging of smaller black holes. Growth. Black holes grow by accreting matter from their surroundings, including gas, dust, and even other stars. Key discoveries and observations. Gravitational waves. In 2015, scientists detected gravitational waves from the merger of two black holes, confirming a major prediction of Einstein's general theory of relativity. Event Horizon Telescope, EHT. In 2019, the EHT captured the first image of a black hole, located in the galaxy M87. This image showed a bright ring formed by light bending in the intense gravity ARU. Interesting facts. Hawking radiation, predicted by Stephen Hawking. This is radiation that black holes are theorized to emit due to quantum effects near the event horizon. Over incredibly long timescales, this could cause black holes to evaporate. Accretion disks. Matter falling into a black hole forms an accretion disk, which heats up and emits radiation, sometimes making black holes visible as quasars. Spaghettification. Objects falling into a black hole experience extreme tidal forces that stretch them into long, thin shapes, a process whimsically known as spaghettification. Black holes remain one of the most intriguing and mysterious phenomena in astrophysics, continually challenging our understanding of the universe. What is the event horizon? The event horizon is the boundary surrounding a black hole beyond which nothing can escape, not even light. It is often considered the surface of the black hole, although it is not a physical surface, but rather a point of no return. Key characteristics. Gravitational influence. At the event horizon, the gravitational pull becomes so strong that the escape velocity exceeds the speed of light. This means that any matter or radiation that crosses this boundary is trapped inside the black hole. One-way boundary. Once something crosses the event horizon, it cannot return or communicate with the outside universe. This makes the event horizon a one-way boundary. Visual effects. To an outside observer, objects approaching the event horizon appear to slow down and become increasingly redshifted. Their light shifts to longer wavelengths due to the intense gravitational field. Eventually, they fade from view as they cross the event horizon. Scientific significance. Singularity. Inside the event horizon lies the singularity, a point where the curvature of spacetime becomes infinite, and the laws of physics as we know them break down. Hawking radiation. The event horizon is also associated with Hawking radiation, a theoretical prediction that black holes can emit radiation due to quantum effects near the event horizon. Over extremely long timescales, this radiation could cause black holes to evaporate. Observations and discoveries. Event Horizon Telescope, EHT. In 2019, the EHT captured the first-ever image of a black hole's event horizon in the galaxy M87. This image showed a bright ring of light surrounding the dark shadow of the black hole, providing direct visual evidence of the event horizon. Gravitational waves. The detection of gravitational waves from merging black holes has provided indirect evidence of event horizons, as these waves are generated by the intense gravitational interactions near the event horizons of the merging black holes. The event horizon remains one of the most intriguing and mysterious aspects of black holes, offering insights into the nature of gravity, space-time, and the limits of our physical laws. Planets and moons. Planets and moons are fascinating celestial bodies that make up a significant part of our solar system. The 8 planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, each have unique characteristics. For instance, Earth is the only planet known to support life, while Jupiter is the largest, with a mass more than 300 times that of Earth. Planets can be divided into 2 main types: terrestrial, rocky, planets and gas giants. Terrestrial planets. Characteristics. Terrestrial planets are Earth-like planets made up of rocks or metals with a hard surface. They have a solid planetary surface, a central metallic core, mostly iron, and a surrounding silicate mantle. These planets also have few moons and topological features such as valleys, volcanoes, and craters. Examples: Mercury, Venus, Earth, and Mars. Gas giants. Characteristics. Gas giants are large planets composed mostly of hydrogen and helium. They do not have a well-defined surface and are characterized by their immense gaseous mass. Gas giants have thick atmospheres, strong magnetic fields, and ring systems. They also have numerous moons. Examples: Jupiter, Saturn, Uranus, and Neptune. Moons, or natural satellites, orbit planets and vary widely in size and composition. Earth's moon is the 5th largest in the solar system and plays a crucial role in influencing our planet's tides. Jupiter and Saturn lead in moon counts, with Jupiter having 79 known moons, including the largest moon in the solar system, Ganymede. Saturn's moon Titan is notable for its thick atmosphere and lakes of liquid methane. Beyond our solar system, exoplanets are planets that orbit other stars. Some notable examples include Proxima Centauri b, the closest known exoplanet to Earth, located about 4.2 light-years away. It orbits the star Proxima Centauri and is within the habitable zone where liquid water could exist. Kepler's 186f, an Earth-sized exoplanet located about 500 light-years away in the constellation Cygnus. It orbits within the habitable zone of its star, Kepler 186. TRAPPIST-1e, one of 7 Earth-sized planets orbiting the ultra-cool dwarf star TRAPPIST-1, located about 39 light-years away. TRAPPIST-1e is considered one of the most promising candidates for habitability. WASP-12b, the gas giant exoplanet located about 1,400 light-years away. It is known for its extremely close orbit to its star, resulting in a very high surface temperature. Moons outside our solar system, known as exomoons, are harder to detect but equally fascinating. Some notable examples include Kepler 1625b, a potential exomoon orbiting the gas giant Kepler 1625b, located about 8,000 light-years away in the constellation Cygnus. This exomoon is as large as Neptune and orbits a planet several times more massive than Jupiter. These celestial bodies not only provide insight into the formation and evolution of our solar system but also offer potential clues about the conditions necessary for life. Astrobiology. Astrobiology is the multidisciplinary field that explores the origin, evolution, distribution, and future of life in the universe. It integrates biology, astronomy, geology, and chemistry to understand life as a universal phenomenon. Astrobiologists study extreme environments on Earth, such as deep-sea hydrothermal vents and acidic hot springs, to understand how life might exist on other planets and moons. They also investigate the potential habitability of celestial bodies within our solar system, like Mars, Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, which may harbor subsurface oceans. The discovery of extremophiles, organisms that thrive in extreme conditions, has expanded our understanding of the possible range of habitable environments. Additionally, astrobiologists search for biosignatures, which are indicators of past or present life, in the atmospheres of exoplanets. Missions like the Mars rovers and the James Webb Space Telescope play crucial roles in this research by providing data on the chemical composition and physical conditions of distant worlds. Through these efforts, astrobiology seeks to answer profound questions about whether life exists beyond Earth and what that might mean for our understanding of life itself. The important discoveries in astronomy. The history of astronomy is marked by a series of groundbreaking discoveries that have profoundly shaped our understanding of the universe. From ancient observations to modern technological advancements, each milestone has contributed to the rich tapestry of astronomical knowledge. Below is a timeline highlighting some of the most significant discoveries in this fascinating field. Antiquity. 750 BCE, Mayan astronomers discover an 18.7-year cycle in the rising and setting of the moon. 585 BCE, Thales of Miletus predicts a solar eclipse. 467 BCE, Anaxagoras explains eclipses and describes the sun as a fiery mass. 270 BCE, Aristarchus of Samos proposes the heliocentric model, placing the sun at the center of the universe. 240 BCE, Chinese astronomers record the earliest sighting of Halley's Comet. 140 CE, Ptolemy publishes his star catalogue, endorsing the geocentric view of the universe. Middle Ages. 400 CE, the Hindu cosmological time cycles in the Surya Siddhanta provide an accurate estimate of the sidereal year. 964 CE, Persian astronomer Abd al-Rahman al-Sufi describes the Andromeda galaxy. 1054 CE, Chinese astronomers observed the supernova that created the Crab Nebula. Renaissance. 1543, Nicolaus Copernicus publishes De Revolutionibus Orbium Celestium, proposing the heliocentric model. 1609, Galileo Galilei uses a telescope to observe the moons of Jupiter, supporting the heliocentric theory. 1687, Isaac Newton publishes Principia Mathematica, describing the laws of motion and universal gravitation. 18th and 19th centuries. 1781, William Herschel discovers Uranus, expanding the known boundaries of the solar system. 1846, Johann Galle and Heinrich d'Arrest discover Neptune based on predictions by Urbain Le Verrier. 1868, Pierre Janssen and Norman Lockyer independently discover helium in the solar spectrum. 20th century. 1924 – The Edwin Hubble proves that the Andromeda Galaxy is a separate galaxy, not part of the Milky Way. 1930 – Clyde Tombaugh discovers Pluto. 1965 – Arno Penzias and Robert Wilson discover the cosmic microwave background radiation, providing evidence for the Big Bang theory. 1995 – Michel Mayor and Didier Queloz discover the first exoplanet orbiting a Sun-like star. 21st century. 2004 – The Cassini-Huygens mission provides detailed images and data on Saturn and its moons. 2012 – The discovery of the Higgs boson at CERN confirms the existence of the Higgs field, which gives particles mass. 2019 – The Event Horizon Telescope captures the first image of a black hole in the galaxy M87. The search for extraterrestrial life. The ultimate goal of exoplanet research is to find unmistakable signs of life. This involves analyzing atmospheres, using techniques like transmission spectroscopy to detect gases that could indicate life. Exploring nearby star systems, mapping nearby stars to identify the best candidates for habitable planets. The search for exoplanets and extraterrestrial life not only helps us understand our place in the universe, but also brings us closer to answering the profound question: are we alone? Please remember to subscribe, like the video, and share it with your friends. Your support is greatly appreciated.